And good evening, AP Physics students. Mr. Gerson coming at you here with a problem from our first problem from Chapter 18, talking about circuits. Ooh, circuits, good stuff. Great chapter, very applicable. Okay, let's dive in. Problem 6 says, I have a hair dryer that draws a current of 7 amps. And when we plug it into the wall voltage is 120 volts. What is the resistance of this hair dryer? And if we let the hair dryer run for 15 minutes, how much time or how much charge would run through the hair dryer? Do people really dry their hair for 15 minutes? That seems like a lot of time. Anyway, let's get going with this problem. Mr. Gerson, this is all new. What do you mean? Current, resistance, what is going on? Well, let's draw a circuit here, how a scientist would draw a circuit. So this is how we draw a battery. I don't know, it's our symbol for battery, two parallel lines like this. This is some type of wire, and then whatever the device is that's using the energy, a light bulb, a resistor, a hair dryer, an engine, gets some squiggly lines, okay? So all, circuits have to have some voltage source. If it's a direct current circuit, like a battery, the current just flows one way. As it turns out, our walls have alternating currents where the current switches back and forth 60 times a second. We're not going to talk about those. We're just going to talk about direct current circuits. So I've got a battery. I've got a wire, I've got some type of resistor. Again, think light bulb or hair dryer or engine or something that's doing something for us. It could also be just, wires have a certain amount of resistance to them, usually kind of small. Okay. So in this circuit, we have current I flowing. And the SI unit of current, we represent current with a capital letter I, is the amp. And current is defined as the flow of charge, or the amount of charge that flows through a circuit in a certain amount of time. So current should have the units of coulombs per second, and 1 amp, or 1 ampere, is defined to be 1 coulomb per second, and we abbreviate the SI unit for current, the amp, with a capital letter A. All right. So I suppose we should define this here. Current. What is the current? Besides 89.3, my favorite radio station. Current is the flow of charge. All right, from one place to another. Okay. So flow of charge. So in chapter 16 and 17, we are doing with electrostatics. That is, for the most part, charges were in a stationary position, or you could assume they were stationary. They were, but now we're starting to deal with the flow of charge. One other thing I should talk about here that's a little bit confusing. We have a convention with current. And the convention goes like this. Traditional current, the convention is that current charge flows through a circuit in the direction positive charges would move. So for instance, here in this circuit diagram here, I have the positive terminal of the battery here, the negative terminal here. Current, or the charge flows, current goes around the circuit this way. Now, some of you who have studied a little, chemistry or whatnot might say something like this. Mr. Gerson, isn't your convention 100% wrong? I mean, really, it's electrons that are moving. The protons don't move. So when you say the current is moving this way and that positive charges are moving this way, isn't that 100% false? Wouldn't electrons really be flowing this way? And you're correct. You're absolutely correct. The story goes that Benjamin Franklin knew that either the positive charges moved or the negative charges moved. He didn't know which one, so he picked one. And we haven't really changed that convention because, well, it's not nice not to carry a negative sign around. So anyway, when you're asked on the AP test what direction is the current flowing, it is flowing from the positive terminal to the negative. If he asks you what direction the electrons are flowing, it would be the opposite direction. So a little bit confusing there. Okay. So we know about voltage, we know about amps now. Let's talk about resistance. All right, that is, if I don't have too much resistance to that idea. Okay, certain things more easily conduct charge and have current flow through them than others. Something with a high resistance is something like a plastic, or something with a low resistance is something through which charge easily flows, like a metal. So the SI unit of resistance is the ohm, and we abbreviate it, ohms, with the capital Greek letter omega. Excuse me. There's just too many O's floating around, so we use the Greek letter omega here. So the SI unit of resistance is the ohm. If this resistance had a resistance of 1 ohm, okay, and this voltage, this battery had a voltage of 1 volt, we would get 1 amp of current through this system here, okay? And what I just described to you is known as Ohm's law, which states that the current in a circuit is directly proportional to the voltage and inversely proportional to the resistance. In other words, if I doubled the voltage in this circuit, right, I would double the current, which makes sense. Put 2 batteries in the system instead of 1, you would double the current. On the other hand, if I increased the resistance, made a resistor that's twice as big, hampered the flow of charge a little bit. If I made the resistance twice as big, the current would be half as much. I kind of think of Ohm's law as kind of like the Newton's second law of the electricity and magnetism world, right? How fast something's moving is equal to the force. You double the force, you double how much it's accelerating, how much it's moving. And of course, the bigger the mass of the object. What is mass? It's resistance to changes in velocity. So anyway, this is the Ohm's law, states that the current in a circuit is directly proportional to the voltage, inversely proportional to the resistance. Okay, let's get to work here. Part A says solve for the resistance of this hairdryer. So we'll use Ohm's law and rearrange it here. The resistance of the hairdryer is the voltage divided by the current. And if we divided that out, we would get a resistance of 16 ohms. So the answer to part A is the resistance of our hairdryer is 16 ohms. Part B, how much charge flows through the hairdryer circuit? Well, if it's on for 15 minutes, I would want to figure out how many seconds that is. So in 1 minute, of course, there are 60 seconds. And we just figured out that the current is 7.5 amps, or 7.5 coulombs of charge every 1 second flow through the circuit. All right. So if we just multiplied that out, we would get a charge of 6,800 coulombs. Okay. So just a little dimensional analysis there with our units. All right. All right, nice work, AP Physics students. I am going to let you go here so you can get on with the rest of your this. Mr. Kirsten, what is that? Well, this is your ohm work. I'm going to let you get on with your ohm work. There's your joke of the day. All right, nice work, AP Physics students. We'll see you tomorrow.